Okay, so now we have measured the force acting on my red ball, red sphere, in terms of the units that I invented. I mean, the meter here is not the real meter. It is, the meter is just kind of this length is the meter that we have in these numbers. But let us just stick with that definition of the meter. And now we have the force. We know how the object moves. Now the next thing is, let's calculate the work done on the object by this force. This is the net force acting on my mass. Now, I know that we had already measured that this is more or less the trajectory. This is the parabola. At this point, there is this force F acting on my mass with this magnitude. And it is displaced in this time interval. It is displaced by this amount. Let me take some numbers. So this is the time, the first column. The second time is the x coordinate. The third column is the y coordinate. Now the whole experiment lasts, whole measurement lasts less than 1 second. So let me do one thing. At t equal to 0, now let me start with, at this point, it is t equal to 0.1 seconds. The x coordinate is 0.995 t in seconds, x in meters, y in meters. At t 0.1 meters, 0.1 meters, the x coordinate, now at t equal to 0.0, my x coordinate is 0.995. My y coordinate 0.705. At t equal to 0.1 seconds, at 0.1 is somewhere over there. It is over here. 0.102. The x coordinate is 0.602. The y coordinate 1.205. Now the reason why I didn't take successive times is that if you, as we did before, if you look at time t equal to 0 and t equal to 0.09, the displacement is around 2.5 centimeters. Now if you consider my ball, it has a radius of 2.5 centimeters. My error bar in measurement of the coordinate is around 2.5 centimeters. We can say at around 2.5 centimeters. So I cannot really say that the displacement is 2.5 centimeters. It should be 2.5 centimeters plus minus 2.5 centimeters. That's a very large error bar, relative error bar. But now if I take the at t equal to 0 with, compare t equal to 0 with t equal to 1, the displacement is kind of around 40 centimeters. 40 centimeters plus minus 2.5 centimeters, that is not a large error in the measurement of the displacement of my object. In the y coordinate, it goes for, the displacement is 0.50 centimeters. Again, 50 centimeters plus minus 2.5 centimeters is small. 0.1, well, 0.2 seconds. It's over here. Now the x coordinate is 0.28, 0, and the y coordinate is 1.503. Now let me write the displacement vector between these two times. Now between these two times, okay, the x coordinate went from this number to this number, so the change is minus 39.3 minus 0.393 meters in the x-hat direction. The change in the y coordinate is 0.533500 meters in the y direction. This is the displacement of my object between time t equal to 0 to t equal to 0.1. Now the displacement between time t equal to 0.1 to time t equal to 0.2 is, okay, so the difference of this one minus this one would give me minus 0.318 meters in the x direction, plus this minus this one, 0.298 meters in the y direction. This is the y displacement. Now you see, the difference in the x coordinate between these two times is 8 centimeters. So the time interval is the same. So if it's a motion with constant velocity, it should have been 0. These two should be equal. But if we know that this number has an error of 2.5 centimeters. This number has an error of 2.5 centimeters. The difference has an error of 5 centimeters. So this number over here is uncertain by 5 centimeters. Similarly, this number is uncertain by 5 centimeters. So within those error bars, if I subtract this one from this one, I get 8 centimeters. But the error bar in that difference is now 10 centimeters. So it is the difference between the displacement along the x direction in these two time intervals is 8 centimeters plus or minus 10 centimeters, which is consistent with 0. No, you don't agree? Is this point clear? The error bars. So if I have some number, some measurement, which gives me x plus minus delta x, and another measurement, x plus minus delta y, the x0, x1. Now x0 plus or minus x1 has an error bar plus or minus delta x0 plus delta x1. When you add two different measurements, the error bars add or subtract two different measurements, the error bars always add. You never subtract the error bars. They always add to your final error in your measurement. So this number we obtained by subtracting two numbers which had an error bar of 2.5 centimeters. So this number has an error bar of 5 centimeters. This number also has an error bar of 5 centimeters. So the difference of these two numbers, which should be 0, has an error bar of 10 centimeters. Well, the difference of these two numbers is 8 centimeters. So we can say that the difference of this one, minus 0.393 meters, plus minus 2.5 centimeters, no, minus 5 centimeters, plus or minus, no, minus 0.318 meters, plus or minus 5 centimeters. This is equal to, well, if I subtract this one from this one, 7.5 centimeters plus or minus 10 centimeters. So these two numbers, within error bars, they are equal to each other. So that is what we expect. The motion in the x direction should be uniform motion. So the displacement along the x direction in same time interval has to be equal. Yes, questions? I said, well, this is 39.3 centimeters minus 31.8 centimeters. The difference is 7.5 centimeters. So this is the force we have. Let me write it over there. Now the work done, we had defined it as the force times the change in y. In each one of these steps, I can calculate the work done on my mass as I go from t equal to 0 second to t equal to 0.1 second, from 0 to 1, will be, well, delta r, F is always in the y direction, that delta r. Well, so I only pick the displacement in the y direction. The displacement in the x direction doesn't do any work. So it is the force, the magnitude of the force in the y direction times the displacement in the y direction as I go from 0 to 1. This is the work done as I go from 0 to 1. Well, the work done as I go from 1 to 2, well, it will be the same thing. It is the Fy times the y displacement as I go from 1 to 2. I should repeat this throughout the whole process if I want to calculate the work done on my mass throughout the whole process. And then the total work will be nothing but the works done as my object goes from the ith step to the I plus first step. Now, in this case, this force is constant, so that simplifies my calculation because I can just take it out of this summation sign. Let me erase here. Total work is the sum of the works at each step. This is the sum of the y component of the force times the change in y in the ith step. F of y times the changes in the y components in each step. But this change in the y component in each step, if I sum all of them up, I will get the total change in the y direction, total displacement in the y direction. So the total work done on my object will be Fy times delta y. How much the y coordinate of my object changes. Now, if you go back to this example, okay, I need my calculator. So the force we already calculated, it is 0.32 newtons. Delta y in this, as I go from the t equal to 0.0 to 0.1, I had just calculated it to be 0.5 meters. So the work done is 0.16 Newton meters. This is the work done in the first step. In the second step, okay, the force is the same, 0.32. But this time the y displacement is 0.298. So the work done in this step is 0.0, let's put one more 0 here, 95 Newton meters. Now the net work done on my mass as I go from 0 to 2 will be just the sum of these two, and that would give me 0.255 Newton meters. By the way, this is nothing but Fy is Fy times, well, if I just take the total displacement in y, 0.798 meters. So rather than calculating at each step, I can just calculate the total displacement in y, calculate the force along the y direction, and that will give me the force, the work done on my mass as I go from time t equal to 0 to t equal to 0.2. It is this formula, this final result we have over here. Now this unit, newtons per meter. Okay, so Newton meters, that is the unit of the work. Since we are using it quite often, we just give it a different name. It is what we call the joule. Joule, 1 joule is defined as the 1 Newton per meter, 1 Newton meters. Now let us do one more thing. So we had already calculated the work done. At t equal to 0, 0.0, the velocity of my object. Well, we already have the velocities here. So this is the y component of the velocity. This is the x component of the velocity. This is equal to minus 3.35 meters per second in the x direction, plus 4.93 meters per second in the y direction. This is the at step 0, at the start of the t, at t equal to 0.0. Now the speed at t equal to 0.2, let's denote it by v2. This is equal to, well, here I have to put 0.2 minus 11.30 times 0.2 plus 4.93. It is 2.76. Well, the y component is 2.76 meters per second in the y direction. And in the x direction, it is again minus 3.35 meters per second. Let me calculate the difference of these squares. You all know what kinetic energy is. So we know that the kinetic energy of an object is 1 over 2 mv squared. What I would like to do is calculate the change in the kinetic energy of my object as I go from t equal to 0.2 to t equal to 0, from t equal to 0.2 to t equal to 0.2, 0.0 to 0.2. So the change in the kinetic energy, 1 over 2, the mass is 2.8 times 10 to the power minus 2 kilograms. Now the change in v squared is the change in the x component of velocity squared plus the change in the y component of the velocity squared. Well, the x component doesn't change. So the change in the x component, this is 0. The y component, the velocity here changes, and the final value is 2.76 squared. This is equal to 1.4 10 to the power minus 2 kilograms. This is 0. Now the final velocity is 2.79. The square of it is 7.7 meters squared per second squared. This is this number squared minus 4.93 squared, 24.30 meters squared per second squared. the difference is, well, if this is 16.6 meters squared per second squared, if you multiply it with 1.4, 23.24 meters squared per second squared kilogram. Well, this I can also write as kilogram meters per second squared times meters, well, the unit. Kilograms meter per second squared is what we had defined as the Newton. This is Newton meter, so this is what we have the joule. Well, here times 10 to the power minus 2. And by the way, I missed the minus sign. So, (7.7) is 2.76 squared. So this is 0. I'm calculating this one only. This is the final value of Vy squared. This is the initial value of Vy squared. So the change in the kinetic energy is minus 23.24 times 10 to the power minus 2 joules. Delta T is minus 0.23 joules around. Well, let's look at the work done. We had calculated the work done during the same time. And we had found that the work done, no, I made a mistake there. Delta y is, Fy is negative. Delta y is positive. So this number here is negative. This number here is also negative. So the work done is also negative because my object is moving upwards, whereas my force is downwards. So if you have two vectors pointing in opposite direction, their scalar product will be negative. The work done during the same time is minus 0.26 joules. Well, if you consider the error bars we have, I didn't write the error bars, but the error bars will be much larger than this difference. So within error bars, in our trajectory, in our projectile motion, we have the equality of the change in the kinetic energy is equal to the work done on my object. So this is the experimental proof that the work done on an object by the total force acting on my object is equal to the change in the kinetic energy of my object. So if you are doing a negative work on the object, the kinetic energy is decreasing. If you are doing positive work on the object, the kinetic energy is increasing. And this is quite a general result. The change in the kinetic energy is equal to the total work done on the object. Now, when we were discussing the force, the work, when we defined the force, okay, this is our definition of the force. There are many forces that can act on an object. And for each one of these forces, you can define some work. For example, if you consider me sliding this book from one point to the other point, the forces acting on this object, what are the forces acting on this book? There is the friction, gravity, its weight, the normal force, the push. Well, there are all these four forces. And each one can do differently. And we can talk about the work done by each one of them. I can talk about the work done by my hand, which will be positive because the force and the displacement are in the same direction. We can talk about the work done by friction on my book. It will be negative because the friction force is in that direction, whereas the displacement is in the opposite direction. We can talk about the work done by its weight. It will be 0 because weight is pointing downward, whereas the displacement is perpendicular to it. Then we can talk about the work done by the normal force, which is also 0. The normal force is not doing any work because the displacement is horizontal to the surface, whereas the normal force is perpendicular to the surface. So we can talk about all these four kinds of work done by various forces. Now, the change in the kinetic energy that we have in this energy work relationship is the work done over there is the work done by the net force, not by a single force acting on my mass, but the net force acting on my mass. If you just take the work done by my hand, we know that it is positive, but at the beginning of the motion, at the end of the motion, the kinetic energy of my book is the same, so there's no kinetic energy. So it seemed if we would only consider the work done by my hand, this relation will not hold, because my hand does some work, whereas the kinetic energy does not change. Well, the kinetic energy does not change because the work done by my hand, as I take this book from there to here, is exactly equal to in magnitude to the work done by the friction. So those are the only two forces that are doing some work. So those two works are exactly equal to each other, but since one is positive, one is negative, they just cancel each other. The total work done on this book during this motion is 0, and hence the kinetic energy does not change. True. Now, if you consider all this motion, so what is the motion? What is the, let's just take this as the positive x direction and only talk about the components along the x direction. What is the velocity of the book now? The acceleration of the book? Now, I will start moving it. So, until this point, well, just imagine all this motion, but from here to here, in this part, what is the acceleration? Is it positive, negative, or 0? That's what I'm asking. It is positive. So there is a positive acceleration. As you said, the force of my hand is larger than the force of the friction. To create this positive acceleration, I need a positive force. That is my hand. My hand is creating a larger force than friction. So there is a positive net force acting on this thing. The displacement is in the same direction. So the work done in this time interval, as the book starts from here, accelerates until here, the work done is positive. There is a net positive work done on the book. Well, it is also consistent with this relation. There is a net work done on the book. The kinetic energy started from 0, and finally it was a positive number. Now from here, the book is moving from here to here. From here to here, it accelerated, so the force of my hand was larger than the force of friction. From here to here, it moves at constant velocity. So what is its acceleration? At constant velocity. The acceleration is 0 in this time interval. What is the net force acting on it? Okay, so there is one answer over here who says that the net force in this time interval as my object moves at constant velocity is 0. Who thinks it is 0? Who thinks it is positive? Remember, I am pushing the book with constant velocity. So who thinks the total force is positive? There is one answer, great. Another answer, great. Who thinks it is negative? Okay, there is one answer over there. What about the rest? What do you think? So that is an answer. He says, why do you think so? Why? Why? Okay, so, okay, maybe I'm just pushing too much. In this, there is one answer I'm looking for. You said that there is a constant velocity, which means acceleration is 0. So that is the step I was asking for. If acceleration is 0, the force is mass times acceleration. So the force should be 0, the net force. Of course, I'm acting on the book with a positive force. That is the force of my hand. But there's also the force of friction, which is negative. These two should sum up to give 0, to give me a motion with 0 acceleration. So net force is 0. The work done by a 0 force, if you apply no force, then you don't do any work. There is no work done on the book by the net force. The kinetic energy doesn't change. Now the last part of this motion. So it started at rest. It accelerated. It reached some velocity. For some time, it moved at constant velocity. And then from this constant velocity, its velocity went back to 0. So what is the acceleration? Come on, I want to see more. I want you to be more rumorous. Make more noise. So the acceleration is? So the force is? The force is negative, so the force of my hand is larger than the force of friction. Yes? No. Friction is larger than the force of my hand because the acceleration is negative. So I'm creating a positive force, the friction is creating a negative force. The friction force has to be larger so that the net force would be negative, the acceleration would be negative. If the net force is negative, the work done by the negative force is again negative. So the change in the kinetic energy as the book goes from some finite speed to 0 speed is negative. So again, this relationship holds. The total change in the kinetic energy, that is, the kinetic energy first increased, remained constant, then decreased. The total change is 0, delta T is 0. But that is also because the work done on the book was first positive, 0, negative. If you sum them up, you end up having 0 total force. Yes? Well, let us make another experiment. This is my book. So it landed here, the friction started. The only force acting on it in the horizontal direction was friction force. The force that I was exerting on the book was 0. The friction force was non-zero. So it can be larger. The thing is, if you want to have a positive friction force, if you want to have, let's just only talk about the kinetic friction force. If you want to have some friction force, the object has to be moving. If you give an object an initial velocity, then there will be some friction, even if you don't apply any force to your object, because the object is moving to start with. Other questions? Now let us come back to this example. Well, there were two things we had derived along the way. Of course, for the case of gravity. It was a constant force along the y direction. So if we write the weight of an object is minus mass of the object, the gravitational acceleration in the y direction. So this is my mass, m. These are my coordinate axes, y, x. The work done by this weight, omega delta r, this was nothing but minus mg times delta y, independent of whether the motion is a very small displacement or a very large displacement. the work done didn't depend on how we went from one point to the other point. I can also write this equation as minus mg, the y coordinate at the end of the period, at end of the motion, minus the initial y coordinate. This is one thing we had derived about. Well, this we had seen in action for this projectile motion. This is a constant force. So for this constant force, we know that for any constant force, in fact, not only for the wake, this is in general true, where this delta r, the object just moves around. Delta r is nothing but the displacement from the initial position to the final position. So this is what we obtained. Now we had also seen that this was equal to the change in the kinetic energy, 1 over 2 m v2 squared minus 1 over 2 m v1 squared. Now if I just collect everything related with the initial position and initial velocity to one side, and everything related with the final position and final velocity on the other side, we see that 1 over 2 mass times v1 squared plus mgy1 is equal to 1 over 2 m times v2 squared plus 1 over 2 plus mg y2. This holds for weight, for an object moving under only the influence of gravity and no other forces acting on it. So we have such a relationship. So its kinetic energy at the initial point times its mass times gravitational acceleration times its y coordinate at the initial point is equal to the same quantity calculated at the final point. So this is an example of what we call a conservation law. Now the initial point and the final point, we just picked any 2 points along the motion of my object. So this was the trajectory of our object. I just picked this point and this point. At this point, I calculated 1 over 2 mv1 squared. If I would add to it mg times y1 at this point p1, and if I calculate the same thing at the point p2, 1 over 2 mv2 squared plus mg y2, those two quantities calculated at these 2 points, they are equal to each other. Well, we can generalize this. If I had calculated for any other point along the trajectory of my object, that thing, 1 over 2 mv squared plus mgy, is something that is the same along the trajectory. It doesn't change as we go from one point to the other point on the trajectory. Of course, the speed of my object changes as I go from one point to the other point. The y-coordinate of my object changes from one point to the other point, but those two changes are such that this combination is always the same. From where to? Now here what I do is I just first fix a coordinate axis, fix its origin. This is the x, this is the y. This point has some y coordinate y1. This point has some y coordinate y2 with respect to this origin. Of course, if I move my origin to some other point, I will have different y1 and different y2. So this combination will be different if I choose a different coordinate axis. But still, within that coordinate axis, once I choose that coordinate axis, this number that I calculate at this point will be equal to the same number I calculate at this point. What this number is does depend on which coordinate system I choose, which reference frame I use. It will be dependent on the reference frame, but once I fix my reference frame, along the trajectory, that number will be same at all points. Yes? Can you speak a bit louder? Another minus 2 points for me, plus 2 points for you. This is not a vector. Here I have two vectors. The scalar product of two vectors is a scalar, is a number. Remember, we had calculated the work as 0.23 joules. This is just a number, not a vector. For a vector, we need at least 2 or 3 numbers, not just one number. Any other questions? Yes. Which one? For book, okay. True. Constant velocity, the acceleration should be 0. Well, let's see. Now, when I push my book, you agree that there is a force I'm acting on the book. I'm exerting a force on the book. Well, I can control the force. I can exert a very small force, very large force. That is, depends on me. I choose how big a force I should apply. There is also the friction force. I know that the friction force is constant. It has the same value, whether my object is moving very fast or very small. As long as it is moving, its value is constant. Well, I can just adjust the force that my force exerts, my hand exerts, to be equal to that, the force that the friction exerts. So I can make sure that they both are equal to each other. Well, the best way to measure it is that if I make sure that my hand moves at constant velocity along the trajectory, I know that the velocity is constant, so acceleration has to be 0. So the net force has to be 0. So if I move my hand at constant velocity, I'm kind of making sure that the force I exert is equal to the force of the friction. Any other questions before we give another break? Okay, 10 more minutes.